how do we make any sense of the world around us? It's simple, really. We measure it. Today, we're going to dive deep into the fundamental language of physics, units. This is how we describe everything, and I mean everything, from the tiniest atom all the way up to the largest galaxy.
But have you ever really stopped to think about that? How do we all just agree on what a kilogram is or what a meter is? It sounds like a simple question, but trust me, it's a way bigger and more important deal than you might think.
So let's just jump right in. First up, we need to understand why we even need a common language for reality. Because as you can probably guess, without one, things get really chaotic really fast.
I mean, just imagine it. Try building a bridge if your idea of a foot is different from the engineers right next to you. Good luck. Or what about trading goods if a pound meant one thing here and something totally different in another country? Our entire modern world, from engineering to global trade, even to launching a satellite, it would just grind to a halt.
So what was the fix? Well, for science to work, for it to be repeatable, for its laws to be truly universal, physics basically needed a global recipe book. A set of perfectly clear, defined ingredients that anyone, anywhere on Earth, could use and get the exact same results. And that recipe book, well, that became our shared system of units.
So what does this universal recipe book actually look like? Well, it's the world standard, the International System of Units. You've probably heard it called SI units.
Okay, now this is fascinating. What you're looking at here are the 7 fundamental building blocks of, well, physical reality. We've got the ones we all know and use every day, the meter for length, the kilogram for mass, and the second for time. But the system is made complete by 4 others that are just as crucial. You've got the ampere, which measures the flow of electricity that powers our world. Then there's the Kelvin, which gives us this absolute scale for temperature. You need that for understanding everything from distant stars to superconductors. And the mole. That's the chemist's secret weapon for counting huge numbers of atoms. It's truly amazing that every single physical thing we can measure can be built from just these 7 basic units.
Of course, the SI system, which is based on that meter, kilogram, second framework, isn't the only game in town. You've got the CGS system, which uses centimeters and grams, and then there's the British engineering system with its feet and, get this, slugs for mass. Yeah, slugs. But to make sure everyone's on the same page, the SI system is the standard for science. It means a physicist in Tokyo is speaking the exact same mathematical language as one in Geneva.
And just to give you a feel for the incredible scale these units can handle, let's talk about the mole again. It's how chemists count atoms, right? And it is a gigantic, mind-boggling number. How big? Well, this quote puts it into a cosmic perspective. There's about 1 mole of stars in the entire observable universe. Think about that. It's a single concept that connects the microscopic world of atoms to the vastness of space itself.
So we know what the units are, but how do we actually use them? Well, this brings us to the physicist's toolkit. It's time we learn how to really speak the language of units.
Okay, one of the most powerful tools in that whole toolkit is something called dimensional analysis. Think of it like a built-in spell checker for your math. The rule is super simple. The units on one side of an equation have to match the units on the other side. So if you're trying to calculate a distance and your answer comes out in, say, kilograms, you know with 100% certainty that you've messed up somewhere. It's an instant red flag.
Let's see it in action. Say we want to convert 60 miles per hour into feet per second. We do this by multiplying by the number 1 in really clever ways. First, we multiply by 5,280 feet per 1 mile. Since 5,280 feet times 1 mile, we're just multiplying by 1. But look, the miles unit on the top cancels out the miles on the bottom. Poof, gone. Then we do it again for time, multiplying by 1 hour per 3,600 seconds. The hours cancel out. All the units we don't want just vanish, leaving us with exactly what we were looking for. It's so elegant.
And you know the best part? This isn't just some abstract physics trick. This is the exact same logic you use when you're on vacation and need to figure out how many euros you get for your dollars or how many gallons are in a liter. It's a universally useful skill for just navigating the world.
All right, let's take all this theory and put it into practice. For our last section, we're going to apply what we've learned about units to a concept we can all feel and understand: density. It's a perfect real-world example of how mass and volume come together.
So what is density? It's really just how much stuff, or mass, is packed into a certain amount of space or volume. We figure it out by taking an object's mass and dividing it by its volume. And check out the SI units.
kilograms per cubic meter. This is what we call a derived unit because it's built directly from two of those fundamental units we saw earlier, mass and length. See how it all connects?
This table really puts it all into perspective. You've got air, which has a super low density. Water is our baseline, right at 1 gram per cubic centimeter. But then you get to metals like gold and osmium, which is the densest naturally occurring element. It's over 22 times denser than water. That's exactly why a small gold bar feels so surprisingly heavy in your hand. It's an incredible amount of mass packed into a tiny little space.
So there we have it. We've built a language to measure the world around us and describe the basic properties of matter, like its density. We can now describe the what, but what happens when we introduce some action? What happens when we start to push on that object and get it to move? Well, that's a whole other story. A story about forces and motion, and that's exactly what we'll get into in our next explainer.